cost exactly. Why is this an issue? What the honey on? Tumi-san, how are you?
Yes, how are you?
Good, and you? I just want to figure out why nobody else can join, or why you're the only one here. Plus, I
It
can't
doesn't show
see
on
my,
ClickUp. It only shows on the Blackboard app on my phone.
it doesn't show
The
on
link
ClickUp.
to
What do
the
you mean?
session is not there on ClickUp yet.
Why is that the case? Shouldn't that automatically go to ClickUp?
I am not sure, so it's only showing on my Blackboard app on my phone.
All right, if you just quickly phone, so let's figure out what is going on.
So I
Okay.
also realized that. So
You just make a quick
on
phone
my,
call and see to figure out what is going on. So, we gaan dit. Ekskuus ek klop ek sny probeer net die Blackboard collaborate my lesing nou gee, want ek gee nou die lesing. Maar daar's twee goed wat nou vreemd is wat nie gebeur het op die toets het voorheen nie. Is ek kan my video nie geshare het vir een of ander rede nie. Ander ding is die studente sê daar's nie 'n link na die of klik op na die sessie toe. Moet ou eksplisiet 'n link share of 'n ding of okay, so sommer net 'n toelink. Ja. Toelink. Ja, okay. Okay. Okay, okay. Okay, okay, okay. Wel, en waar staan jy daai settings? Okay. Maar ding is dit wat weet is dit gewerk, ek het laasweek getoets en dit gewerk. En nou eers keer ja. Okay. Okay, nee, cool. Okay, thanks. All right. Ek sal kyk hoe dit uitsorteer. Dankie. Okay, dankie. Okay, totsiens. Okay, bye bye. All right, so let me get the outcome. All right, let's just see what's going on. So hopefully, so I've submitted the link now to click up, so everybody should be able to see that soon. You should get that in the mail. I just need to figure out why my video is not sharing. What is the restriction here? What is going on? Ish. No, this is not good. So what is going on here? All right, so I'm just, for some reason, I tested this last week and I could see myself, my screen sharing everything. And now that for some reason, my video is not showing. Showing? All right, finally that's now working. All right. So I ask, can everybody see the light board? And then the question is the light board the wrong way around? Should I flip it? Because I think there's a difference between Google Chrome and what's going on.
It's the right way around, sir.
Is it the right way around? Okay, thank you. Just want to double check that. All right, so let's just wait a couple of seconds. Apologies for the chaos now. I was not aware that I should share a link or a tool link for Collaborate, but now luckily that's on. So I'm just going to wait a minute or two. But anyway, so let's check where we were. This is essentially what's on the board is where we stopped our last lecture. And essentially what we did is we just derived the expression for the vertical displacement for our given problem, where we had sort of a clamped beam with a distributed load Q applied, length L, Young's modulus E, and a second moment of I. So that's essentially what we derived last time. And as again, just to remind you, once you have essentially the vertical displacement for your problem, we recover the slope, we recover the moment, we recover the shear force and the distributed load based on differentiating this expression. So as we take information away, because when we differentiate, we take information away, we essentially recover the other components from that. Okay, so before we continue on towards statically indeterminate beam problems, I just would like to maybe just quickly demonstrate again differentiation of Python. Just to make sure I give a bit of Python in class every now and then to make sure that we're all comfortable with it. And it's something that all of you would have gone through now in the tutorial. So what I'm going to do here is something that you should be fairly comfortable with. But again, I just want to make sure that everybody's on the same page. Okay, so that's essentially. I'm going to start with a blank slate of Python, so that I can start from scratch. And this is sort of one of the last times I'm going to most probably start completely from scratch. So I don't want to waste too much time typing, but I just want to, in the beginning, develop a little bit what's going on. Again, for those of you that are late to the course, if you want to open up Python, essentially you can enter Anaconda from the command prompt, Anaconda prompt, enter it to a place where you want to open up the Jupyter Notebook, where you want to store your files, and you can open up there, or you can start it from where you are and navigate through the notebook environment towards where you want to be. Okay, so that's essentially this kind of, so I've navigated towards desktop MKM321, week 2. Let's start off with this. So let's import SymPy. That's making sure we're getting some symbolic Python going. So this is again a demonstration of SymPy. We'll be working in that symbolic mode. Let me just run it like this. And all I want to do now is identify what are all the variables we want to define. So we've got a variable for E, I, Q, X, L. So that looks like all of them. So that's after we've used for this boundary condition we had there. So let's say it's again E, I, Q, L, X. Anyone,
Sorry,
anything else I've missed? Yes?
we can't see your screen at the moment with Python going.
Ah, you don't see Python. Okay. You see now?
Thanks.
Wow, thank you for that. Yeah, I do apologize if I am confusing screens. Please don't be shy to remind me. Okay, so all I've done is just import SymPy as SP. I've identified the variables here. Again, I want to show you a shortcut that we don't waste time typing. I'm just typing SP.symbols, making a string by putting those brackets, and I've copied essentially these variables here. And I'm just pasting them there. So Control-C for copy, Control-V to paste, and now I've got the variables defined. So that we don't waste time typing all of these things the whole time from scratch. And now I can define my displacement as minus, this expression I have is, let's just type it the weight on the board, 1 over E times I. All of these things are now variables, symbolic variables that I've defined at the top there, times, and then I've got the minus 1 over 24 times Q times X of 4. plus 1 over 6 times Q times L x to the power 3 minus 1 over 4 Q times L squared times x squared. Which is good to just double check that the lengths are to the power 4. So there's a L, there's a Q, x to the 3, so that's to the power 4. There's an x to the power 4, here's L squared and x squared, so together then to the power 4 for the displacement, for the distance. Okay, so that's essentially what we have there. There's our expression for V, and again, just to remind you how we're going to be operating this course. I'm not going to expect you to differentiate by hand, that's not the aim. I want us to make sure that we can quickly and efficiently solve these problems without worrying too much. So we're going to demonstrate derived by array. Essentially, this is a way we can differentiate symbolically. And so I'm going to give the expression that we want to differentiate, that's V that I've just built up there, and the variable with respect to which I would like to differentiate, and afterwards I'm going to print dv/dx. That essentially is the evaluation of that. Okay, so let's now, after I've differentiated, this is the expression that we have. And you can double check from the beam deflection notes whether the expression on the board is correct, or whether I hope it is, it should be. But essentially, this is our expression that we have for the derivative. Again, you can see there's a negative in front there. If you go back to your beam deflection equation, just open up this. Essentially, see there's the vertical displacement. In this book differentiated, they've got the minus sign, so differentiation is wrong. But again, it's why it's also good to be able to always double check things from first principles. But I can continue this differentiation process. I don't have to stop there. If I want to compute the second derivative of V, so we call it dv dx squared, then I can just give it dv dx, and again differentiate with respect to x, and then I can just print out d2v d2v dx squared. And there's the second derivative that I have. And now we know that's proportional to the moment. And I can continue the third derivative and the fourth derivative in the same way. Okay, so this is just to make sure we're all comfortable with the way we're going to be operating this board. So again, there's not a lot to this, but the important thing about this is just to make sure that you get comfortable doing this, so that you can quickly develop expressions and ask questions. It's now what we have time for, because this took milliseconds to do, or seconds to compute. We have now time to really interrogate what this is telling us. Do we trust what's there? Is there a mistake? Are we happy with what it's saying to us, etc.? So we can compare that then and think critically about that. Okay, so that's just to make sure that we've got just a demonstration class about differentiation, and make sure that you are comfortable with that. Any questions before I continue? Everybody comfortable with this? Okay, so let's wipe the board clean. So this is, I just make sure we end off with continuity from where we were last time. So I'm going to wipe all of this off. And today's lecture is going to be essentially continuing on the beams, but we are going to be focusing on statically indeterminate beams. So that's what the focus area is going to be on. But before I do that, I just want to first talk about how we're going to be approaching this. Ooh, see, there's something that might be okay. Thank you. So the one thing that is for sure is that this board is also a lot of fun for other members in my family. Okay. All right, am I on the right screen? Everybody can see? Yeah, hope so. Okay, so I'm still busy with beams, so I'm going to leave that, but I'm going to put in here statically. Indeterminate. Okay, so that's, just make sure I box it a little bit. Okay. Why is this one struggling so much? Okay. So the bottom line is there's various ways we can approach statically determinate beams, and the approach that we're going to follow in this course, the one I wanna drive home, is by using linear superposition to solve it. And the reason is it allows you to use your beam reflection tables in a combinatorial way to solve more complex problems. But more importantly, it's highlighting this principle of linear superposition, which is a very important concept again when it comes to finite element modeling, as it's one of the principles that you can essentially exploit. So before I start off with statically determinate, I first just want to remind ourselves what is linear superposition. What is this principle? Okay, so essentially, let's say I've got a system, some kind of stress system that I can write as Kx equals to F. So essentially, I've got a structure which we can define by some kind of stiffness relation. So this is something in newtons per meter. This is now just distance meter, and here's forces that I apply to the structure. This is just newtons. So for units, consistent units. And all that linear superposition is essentially telling us is, if I were to apply two loads simultaneously to the structure, I can solve it as the sum of two individual loads that I've applied. And to demonstrate that, let's imagine I'm applying the first load to the structure F1. And essentially, if I were to solve that, I would then solve for U1 as my solution. So I can write that as U1 is K inverse F1. So that's one way how I could go about solving it. And you can think of this K as a multidimensional, it's a single variable problem. Doesn't matter at this stage. It's the principle that I want to just highlight clearly. If I were to apply a second load to the structure, F2, the same structure. I'm not changing the structure. I just get a different force that I apply, but I get a different displacement now because it's a different load. Then essentially I can solve U2 as K inverse F2. And so the whole question is what is the solution if I were to apply F1 and F2 simultaneously to the structure? And linear superposition is essentially the fact that I can recover it from these individual solutions that I've already computed before. And to demonstrate that, I can show you that if I were to compute U3 now as K inverse of F1 plus F2, just make this plus better. All right, this F1, F2, I can then recover out K1, F1 plus K inverse F2. And we know that there is essentially just the displacement U1 and U2. So U1 is K inverse F1, U2 is K inverse F2. Okay, so that is the whole premise of linear superposition. And just as to complete this discussion, I always like to just remind you that the whole point that we can complete this K inverse is based on linear superposition. So this whole idea of a K inverse is essentially, this epitomizes linear superposition. And I'm going to explain to you why I say that. So let's imagine again, I have a structure K, and I'm going to solve now for a specific load that I'm going to apply. Let's say the load, imagine now this K is like a matrix, a multidimensional system. The first load I'm going to apply is the load 1, 0, and 0 everywhere else. So the first place I apply 1, and 0 is everywhere else, and then I solve for this, and I call this solution 1. Then I can apply for the same structure, I can apply the second load. But I choose a very specific load. Again, the loading I choose is this one. And I can continue in this way, as you can see. So S3 is essentially this load. Well, the nice thing is, because we're sitting with a linear system, I don't have to apply only one right-hand side at a time. I can apply many of them. So I can sort of have a matrix of right-hand sides. And instead of getting a single vector out, then I essentially get multiple columns. So each column corresponds to one of the right-hand side vectors that I have. So I can imagine solving this system. S1, S2, up equal to Sn, for instance. Just tell me if I'm going off the board. Am I close? Ooh, it's getting very close. Okay, so essentially I'm going to say equals, but I'll write the right-hand side here. And my loadings that I've applied is 1, 0, 0, 1, 0, 0, etc. And that is just the identity matrix. And so what I essentially have is I have K times these solutions that I found is equal to the identity matrix. And that is the definition of the inverse. Is what can I multiply by K, what matrix can I multiply to this matrix K to get the identity matrix. So that is the inverse that I have. So essentially when we apply an arbitrary loading, we are just taking a linear combination of the loadings we've already solved for in the structural system. So that is important to understand. So this whole idea of writing everything like this, and because it's a linear system and this inverse that we can write out, it really encapsulates the essence of linear superposition to the core. Because essentially what we are doing when we solve the inverse is we are applying these unit loads one at a time, and in the end it gives us essentially the displacement solutions after I've applied each one. So you can also interpret what this K inverse means. It's essentially the displacement solutions for a unit loading that we've applied. And then we can just take a linear superposition of that. When we have an arbitrary loading, not just the one. So if my loading is essentially now something more complex, 10, 4, 2, and 0, 0, what will happen is I will take 10 times S.
Sir, you're
Yes.
below the board there. We can't see.
Am I below the board? All right, thank you for that.
And also, sir, could you possibly make yourself a presenter? Because currently you're only filling up about half our screen.
Am I not a presenter?
No, so in the Blackboard settings, there should be somewhere where you can make yourself a presenter, and then it will share your whole screen.
Okay, thank you for that. It's good to tell me so you can see. So I'm for some reason moderator. Okay, so session settings. So I'm going to change this. I'm trying to figure out how I can change that here to a moderator. Perfect. If you just give me a quick phone call. Just give me 1 second. I'm just going to mute myself quickly. All right. So seems like it's my first phone a friend did not help in terms of how to resolve this. So I can see that I am, for some reason, I'm a moderator and not a presenter. But there's no ways that I have an option to actually change that, it seems here.
Perhaps try remove Eloise as a presenter, and then it might just default you to be a presenter.
So you see. Okay, make a participant. And what am I now? Still moderator, it seems. The funny thing is I can make everybody else something else, but why can't I make myself a presenter? I can make myself a captioner. It's weird. So Eloise is now not a presenter anymore, but a.
Sir, are you currently presenting or only sharing video?
As far as I have it, I'm presenting. So I'm. What is there? You mean there's a huge difference between presenting and sharing a video? Let me take my sharing video off. Let me just double check this. See if I do that. I'm still only. Yeah. So I'm unfortunately still only a. All right, doesn't matter. So I'll need to figure out how we're going to resolve this. So what I maybe want to do is see if this will help if I share, if I hide all the. So this is a new environment, so it's going to take. Unfortunately, this is not great. So I'm going to say only show presenter moderator profile pictures. Is that helping or not when I do this?
There's
how
no
big the screen is? No difference. All right,
But-
thanks for letting me
So
know that.
it's
Yes.
readable for now, so we can finish this
All
lecture.
right, let's continue.
by next
All right.
time.
It gives me time to sort it out then. I'll play with it tonight and see if we can figure out what's going on. Okay, so it's only the bottom that's cut off at the moment. Is that clear? Okay, so let me just do an example here to say here at the top, if I were to apply a more complex load, something like 10, 4, 2, and then 0, 0, 0, what this boils down to is this is saying, okay, so essentially we just take the displacement solution when we applied a loading 1 and zeros everywhere else, multiplied by 10 plus, then we take the displacement solution of the second column, multiplied by 4 plus third one by 2, and then zeros times the rest. And that's essentially what we are doing when we solve a linear system, or when we write down the inverse, is we really leveraging to the extreme linear superposition. Okay, so this is just to make sure that you're comfortable with it. It's something that you've done all along, and it's just a recap because essentially this is what we've done in MSY 310 and MODL 227. All the problems you've solved so far were linear problems instructions. Okay, so let me just wipe this off. Now we've set the scene for the principle that we can apply. Okay, so take this off. Okay, so linear superposition for beams, and what I want us to imagine is, let's say we have got a beam but with the following loading. So I apply distributed load, the one that we solved essentially, so it's nicely clamped. Got some distributed loading on here. It's called a Q. With that distributed load Q. Now the newtons per meter units, and let's say I apply also on top of this, I apply a point load sum, a point load P. And so I can solve this in many ways. I can go by the integration routes, or we can just essentially say, well, we've solved all of these simple problems. So if I've solved this problem once before, we have applied a Q, that's the one we've done before. And if I've sort of solved the displacements for a beam with some loading applied somewhere, and I've already gone through the effort of deriving these two solutions, I can then just leverage essentially linear superposition to solve this problem. So this is not statically indeterminate, this is still statically determinate, but this is just highlighting the principle that we are now going to solve this with linear superposition. Okay, so do another one. Should be nice and clear. Okay, so that's essentially saying applying the Q load, distributed Q load, plus the loading of the P that I've applied somewhere. And if I solve this one, get its displacement field, and I solve this one, get its displacement field, and I just add the two together, I get the solution for that. That is essentially just, again, highlighting linear superposition. So we can solve problems that are statically determinate using linear superposition. That's the simplest thing that we can do, and that's something I believe we've done in MODL 227 to a large extent. And the question is, how can I leverage this idea to solve something that's statically indeterminate? So let's go through the same motions. So essentially, if I have now a problem as follows. a beam that I've got. Just make up something and apply load P here. So that's the problem that I want us to think of how we're going to go about solving it. And again, I can go and say, well, this is a problem that is statically indeterminate. Why? Because if I take a look at sum of moments around here, I can resolve my unknown moment, A. Let's call this point A. Sum of forces in the y direction, I have essentially an unknown force here, Fa. I also have a reaction force here, let's call it B. A reaction force that's unknown here at C. And essentially I've got applied loading P that is known. But I've got 3 unknowns and I've got 1 additional equation to help solve it. So I can't solve this problem. It's just straightforward. Okay, but we can leverage this linear superposition. And the way I can leverage linear superposition is to say, again, same as we did before. We just decomposed it into lots of simple problems. So I can say, the first problem that I want to solve is essentially this one here. I've just got this load P applied here. And then I can say, well, I can solve another problem. The problem here where essentially just imagine this unknown RB. I don't know what it is, but I can essentially say there's another problem which I can solve. And I know how to solve this one, and I know how to solve this one because of my deflection tables exist for this problem. And I can solve it using, I can solve for C as well. If I apply my reaction force here, I can solve the same problem. And now we can ask ourselves, okay, so I've done this, how does it help me? How do I get additional information into the game? Because I still essentially have 1, 2, 3, 4, these 2 reaction forces here. RA, FA, and MA. That's not unknowns that I want to try and solve. Well, what do we know about statically indeterminate is we need to know something about the displacement. So if I just solve these things independently, nothing great's gonna happen. Okay. But what do I know? I need to make sure that in the end, the displacement at point B, the vertical displacement, is 0. So this thing can only roll in the y direction, the x direction. It can't move up and down. It's a roller. And here it's also got a roller constraint. It can not move up and down, it can only move left and right there. So this plus the fact that I'm using essentially what's called compatibility conditions, or it's a fancy word for saying I'm looking at the displacements. And I need to exploit stuff about what I know about the problem. I don't know what the displacement is going to be here up front, or the displacement there, but I do know here where I apply the constraints what the displacements are going to be. So what I need to make sure is that the vertical displacement, so I'm going to just give some names to the vertical displacements that I get from solving this. So I'm going to call this one the vertical displacement A. So this is the solution if I only apply this point. I'm going to call this solution if I only apply this reaction force there, nothing else. The vertical, I'm going to call it the displacement solution, VB. And essentially, if I were to solve this problem with RC applied there, although I don't know what magnitude is, if I were to just look at this solution here, I'm going to call it essentially C. And what I need to make sure of is essentially what I need to make sure of to get additional information is that if I sum the displacements evaluated at this point, so I'm going to give now a distance at this point. So let's say this point here it's got a distance of A. This point here it's got a distance of small b. So if I were to evaluate the VA at x equals to A at that point, plus VB evaluated at x equals to A, plus VC, this solution, also evaluated at x equals to A. I want them to sum equal to 0. That's one equation that I've got, initial equation. And I can follow the same argument by saying if I were to evaluate at x equals to A plus B, all of the solutions here, together their sum must be 0. So that in the end, the final solution doesn't displace there. So I can follow the same argument for the second equation by saying, now I'm looking at where I apply the second load, and this is now at A plus B. So VA, so this displacement solution evaluated at A plus B, plus this displacement solution evaluated at A plus B plus this displacement solution evaluated at A plus B plus B plus B. That's my second equation. So now let's look at how many equations, how many unknowns do I have again. So unknowns are FA, MA, RB, and RC. My equations, so still on the board? Yeah. My equations are essentially the following. Sum of forces in the y direction, that's 1. Sum of moments around any point, let's call it point A, equal to 0, 0, plus equation 1 and equation 2. So here's 4 unknowns, and I've got 4 equations. And now I've got a problem that is easy to solve. By applying exactly the same principle of linear superposition, so what we've done for the statically determined case to solve more complex loading cases, you can think of all of these additional loads that we applied to the problem as just more additional loading cases, more complex loading cases that we apply. Okay, so this is a generic framework then to solve statically indeterminate problems for beginners. And again, it's highlighting this principle of linear superposition, which is a really important principle in finite elements. And also just in general, when it comes to modeling later, we will explore. By exploiting linear superposition, we can save ourselves lots of computational cost and effort. Okay. Any questions up to this point? Is everybody clear on what's going on here? Would you be able to solve this? Let me just quickly talk about one thing before we continue on. I'm not going to solve this now, but I want to just take you to the beam deflection table for this example. So maybe let's quickly just go to the beam deflection table. Bear in mind we're applying a load at the tip of the beam, and we're applying loads sort of in the middle parts of the beam. Okay. So I just want to look at the displacement for a load that's applied somewhere in the middle of the beam. Just want to show you that so that you know what to do when you evaluate these vertical displacements. So I'm going to go now back to my, what is this, my PDF. Is that clear? Can I just confirm it's the right way around?
Yes, so we can see it and it's the right way around.
Thank you. So this is just to remind you of a clamp beam where we applied a load somewhere in the middle of the beam. Okay? And so essentially in this case, when we apply the load somewhere in the middle of the beam, when we look at the vertical displacement, there's essentially a vertical displacement that's given up to the point where we apply the load. That is for x from 0 to a, from 0 to a. And then there's another formula for vertical displacement if we were to look at what was happening to the beam after the load was applied, this b part here. So this is now for x from a to b, or from a less or equal to l. That's that section there. This is the second equation that you evaluate. So obviously when you go back to the example on the board, if I look at this point load displacement right at the tip, it will be essentially that first part of the displacement that we'll be looking at. If I were to look at the vertical displacement here, but in this case here, for this example, we are looking at the vertical displacement, essentially where a load, this RB is applied here to the load. Okay, so for essentially, when I start looking at that formula, that single formula of where I'm applying loads, what I need to just be careful about and cognizant about is when I look at what's going on here for this one, for this equation here, I will be looking at where the loading is applied essentially up and until that point there. If I were to look at exactly the same loading but in the second equation, then where this loading is applied here, then I'm evaluating this beam at the place after where I've applied load. Then I have to use another formula, the second formula. So for the first equation, when I evaluate this first equation, the loading is applied at the place where I am, the sum of the force, the sum of the vertical displacements is applied at the place where I apply the load. So I can use the first part of the formula. But when I start looking at the vertical displacement at this point here, so when I look at this second equation, at A plus B, then essentially I need to look at the the displacement formula will have applied after the loading has been applied. And so that's all that we have to take care of to make sure that we get proper formulas out for the vertical displacement. So for each of the displacement cases, we need to ask ourselves where this loading is applied. So essentially, where we're evaluating the vertical displacement for that load case. So these are the cases where we're applying. So for this RC formula, when I look at the first equation, so if I look at this VC one here, when I look at the first equation, I'm evaluating some of the vertical displacements here. And when I look essentially at the second equation, I'm looking at some vertical displacements there. Okay. So that's just to make sure that we're all on the same page. There are the two vertical displacement formulas. Just keep track of where you are evaluating the sum of the vertical displacements relative to where the load is applied for that case. And then you can figure out which is the right formula to use. Okay, I hope that is clear. Okay, so that's essentially the nice thing about once we've got here, we have now a 4x4 system that we can solve. And again, we're not going to solve this. We can solve this. We can solve this with essentially substitution by putting out variables and substituting into other ones. But I would like to encourage us to solve it as a system of 4x4 because this thing can go up to 10 by 10, or 20 by 20, or 30 by 30. Then you don't want to do a substitution manually for green-line variables. You want to then rather make sure you build up a system of linear equations and just solve a system and move on to go on with your life. Okay. All right. So that is essentially making sure that we have covered now linear statically indeterminate beams and how we would go about solving it. And essentially, you can think of statically indeterminate beams just as a complex load case by leveraging that. The only difference is for the complex load cases, all of those loads that you apply are for the statically determinate case are known. For the statically indeterminate case, some of these loads are unknown. And they are part of the things that you have to solve. And so that's why these equations are helping you. Okay. Any questions before I move on? Is everybody clear on this? Would everybody be able to do this? Can I hear a big yay? No?
Yay.
All right. Thank you for that. Okay. That is fantastic. There's somebody out there. Okay. So I hope I've given you a good taste of how simple these problems are. Statically determinate or indeterminate. If you just think about it sensibly and applying the right tools. You just keep in your head about how to apply the algebra. And again, if we leverage Python to a large extent, these things become trivial to do. Okay. And you'll see this essentially covers one of the last tutorial example problem, where it's a little 6x6 system, 6 unknown 6 equations that you have to solve for tutorials, the last tutorial question, which is one of the example problems that I got from Dr. Ingalls, that apparently some of you have solved in MSY 310 or have looked at in MSY 310. And it's just to make sure we complete the loop and get comfortable solving statically indeterminate questions. Okay. Can I put another problem out? One that's maybe a little bit simpler, but also quite important, and also features in your tutorial for next week. So here I'm applying some loading Q, and what I want to just demonstrate here is, imagine I do the following. I put a spring in here. Okay, so first what I want us to do is to just imagine what's going on here. Normal clamp beam, this is the one that we derived explicitly in this course now. So we've derived the equations. I'm putting my hand in front of it, but I realize it's only me that's not seeing. So imagine, so this is just the thing that we've derived the equations for deflection, the first example in those beam deflection equation tables. This is a solution for that. But all I'm doing is I'm saying, let's add a spring to this. And so this is essentially the underformed length of the spring. So when no load is applied and everything's nice and straight, there is no loading on that spring. The question I want to ask is what happens if I put a spring in with different stiffnesses? How must it look? So the first question we have to ask ourselves, is this a statically determinate or indeterminate problem? And we know that, so we can choose the stiffness for that spring to be K. So it's a known value, same as Q. It's a known loading, same as this distance L, which is a known quantity. E and I are known material and geometric properties of the beam. So my question is easy: can we solve this problem? Does the deflection of this beam at all influence something about the solution? And it's quite easy to see that by actually just modifying the K in your head to say, if I take away the K, then essentially this thing is just that formula that we've derived. If I make the K essentially close to zero stiffness. 0 intermediate stiff. If that's the case, then that thing will form as we've derived the equation for. But if I make this K something that's near infinite intermediate, something that's very stiff, then this problem solution essentially becomes a roller. So that's for this case. It essentially becomes a roller then. It's so stiff that it can't really displace there at all. So that is essentially just two extremes. If you just think about how, if you were to change K, whether the solution would change. And because of that, if I choose any other intermediate value for K, it's going to affect the solution. So this is a pure statically indeterminate. And how? So the question that I want to pose is for ourselves: how can we go about deriving this? So this is just to set the scene. So again, some intermediate K that I might choose for this. So the question is how can we think about this problem? So we can think again about this problem using linear superposition. Start off by saying apply some distributed load. That's the one case, and that will cause this beam to essentially deflect. And this is this maximum deflection here at x of L, so I can call this now, call it VQ for the Q loading at x equals to L. That is essentially the displacement that we have there. I can have the other load case, which is essentially the spring, which is going to apply a force to the beam. So I'm going to call this P, or call it R for reaction R. So that's the reaction there, and then this thing will displace like this, and this distance here I can think of as VR evaluated at L. So that's essentially what I have. And so how do these things two things interplay? What is the load in the force in the spring? What is the load in the spring? So the more the final deflection, so the more the deflection of the Q and the fact that the spring is posing back, if I do the superposition of the two, there will be some gap that will be formed. So if I think about this plus this equals to the final displaced state of this structure, maybe the final displaced state originally there is now somewhere here. Where this is now, let's call it a delta S, the gap of the spring. And there's my spring. So that is the final displacement. So this, if I think about this displacement, I can think of it as if VQ is negative, VQ of L. If I think of VR as a positive, it doesn't matter. I can just add the two together. Say VR at L is essentially the difference. The gap that remains is delta S. So VQ is how much it goes down, some negative value. VR is some smaller value than VQ, but it's some positive value. And then what remains essentially is that delta S. So VQ takes it down to the bottom, for instance, V are only up partially, and then the gap that remains is delta S. And this delta S features in the loading of the spring. So the force in the spring, the action force in this spring, is going to be essentially K delta S. And again, if I look at this, I've got one equation here for K delta S. I can obviously go and expand this a little bit and say K delta S is essentially VQL plus VRL. That is what I have there. That is then how much the things are displaced. Just need to make sure that we keep the right signs. So in this case, the R will be, the way I've drawn the R, it should be positive. So I might have to put a negative in front of this, because VQ is going to be a larger negative than R. It's going to be some smaller positive value. If I think about the things, how it's being applied. So I just want to make sure that the R is indeed in the positive direction, the way I've drawn it there, as R is assumed to be up positive. Okay, so that is in all. That gives me another equation that I have. So to solve this problem, essentially I have got the unknown reactions here, MA and RA, plus I've got this new reaction here, R, that I need to solve this. I've got these three unknowns, but I only have two equations because sum of force and X doesn't really count here. It's only sum of moments and sum of force and y. The two equations, the third equation. That is essentially a new equation that I have here. Third equation to solve. So 3 equations and 3 elements. Just write them again just to make sure clear. So here I'm going to say moment A, RA. So unknowns are MA, RA, and just R. So that's spring reaction force. And the 3 equations is again sum of force and y. This is 0. Sum of force around any point, moments around any point is 0 plus then essentially 1. And there I can solve this as a 3x3 system. Okay, and this is one of the tutorial questions I wanted you to solve. I want you to go through this. And you're welcome to first start solving this by hand. I think we are running out of time. So what I'm going to do is I'm going to solve this by hand tomorrow in class, just to complete some use of the static indeterminate case will be used in the class. I will solve this from by hand in class, do a small, just a quick demonstration of how we can get going in Python solving this. I'm not going to solve the whole thing. I want to leave that for you in the tutorial, but I will just make sure we solve this then by hand. Okay. Just a quick question before we leave. Is there any request to solve the previous question that I've shown? The one where we have the linear superposition of the beams. Does anybody want me to solve that in class by hand on the board, or is everybody comfortable with that material? Can I just get an indication? If there's anybody that would like me to solve that, if you don't want to answer now, just pop me an email and say, Nico, please solve also the previous problem, the one where we essentially had the beam with the 2 rollers. And the reason I'm asking this, I just want to make sure everybody is comfortable with where we are. Does anybody want me to solve this by hand? I can either do it on whiteboard, or I can just do it by hand on pen and paper and upload that solution. But if there's any request for this, let me know. This is something, as far as I know, you should be fairly comfortable with, and it should be actually quite something you've practiced quite a lot. But just let me know about this, and then we can focus on this. Yes, is there any question? All right, I will do that. I'll upload the solution. Awesome. All right, so we talk about the Python. You talk about the Python for this problem here. All right, I will solve it by hand and put it up on pen and paper. I will do that, and then I'll put up a Python solution to this one as well on ClickUp, so that this problem's Python solution and its hand solutions on ClickUp. Tomorrow we'll just solve this one quickly by hand, just to make sure we're all on the same page, and then that sort of concludes the sort of background material for this course, and making sure we're all on the same page. MIW227 and MSY310 should be then sort of on the same footing, because we're going to use these solutions and way of thinking about the problem extensively then to solve sort of more complex, or to at least compare our FEM solutions to against. But again, it's going to fill the background for how we're going to develop the mathematics that's behind the fundamental method. Okay. So this week we'll start already with the continuum mechanics kind of thinking about stress fields, strain fields, displacement fields in 3 dimensions. So that's what we will start doing later this week. Okay. Thank you for that, and I'll see everybody at tomorrow's lecture. Thank you. All right, have a good one. Bye.